Greetings and welcome to Mr. Van Lowe's poorly monetized low-budget science channel. Do not click like, do not subscribe, unless you really have to. Okay, here's topic 3.1. This is the second lesson for thermal concepts, and let's get into it. Our learning objectives today: by the end of this lesson, you will be able to describe phase change in terms of molecular behavior, sketch and interpret phase change graphs, and calculate energy changes involving specific heat capacity and specific latent heat of fusion and vaporization. And I recommend that you do a lot of practice calculation for this topic. A lot. You want to be very familiar with the algebra. Okay, so phase changes occur when a substance changes its state due to formation or breaking of chemical bonds. So the way that these chemical bonds are allowed to form is by increasing or decreasing temperature. So if we increase temperature, that's going to excite our atoms, increase their kinetic energy, and that's going to cause chemical bonds to break. So we're adding energy to the system. Decreasing temperature slows down our atoms. That decreases kinetic energy, and chemical bonds will form. They kind of snap together electrostatically, or like magnets. So when a substance has completely changed its state, the phase change is complete. So phase change is our transitional state of matter. And here are some examples. We've got melting, which increases energy in the system. So chemical bonds are broken, and the transition for melting is from solid to liquid. No surprise. Vaporization also increases energy in the system, and chemical bonds are broken again, and we're going from a liquid to gas here. Sublimation is not something you'll have to deal with in IB physics, particularly just because the mechanism is a little complicated, and we tend to keep things simple for IB physics mostly. Deposition is the opposite of sublimation, so it's when gas transitions directly to a solid. Here again, though, we're increasing energy in the system for sublimation. Chemical bonds are broken. We're going from a solid to a gas. Okay, condensation and freezing both form chemical bonds, both decrease energy in the system. Condensation goes from gas to liquid, and freezing goes from liquid to solid. No surprises. So a couple quick examples of room temperature sublimation would include carbon dioxide or dry ice, as well as iodine, which forms a nice, cool purple gas from the solid iodine crystals. It's pretty awesome. And okay, so when we add energy at a constant rate to a system over time, the temperature of a substance is going to change like this. So this is what we get. We get heating of the substance, the temperature is increasing over time, and then it stops increasing while the substance is melting. The temperature stays consistent until all of the substance is melted. Then our liquid will continue heating until it hits the boiling point of the liquid, at which point all of the liquid will transition to a vapor or gas. And again, our temperature is constant until all of that liquid is gone. So think of water boiling at 100 degrees Celsius, and you've got it. Okay, then we can continue heating our gas, but that's it. We could see a fourth state of matter on here called plasma, but the transitions from various states to plasma are, again, a little more complicated than we get into for IB physics. So temperature does not change. Yeah, we've covered that. So what's happening here? Why is our temperature not changing during these periods of time? What's going on? So you can pause the video if you want. You can take it over. Dun, 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 dun. Jeopardy theme song. Okay. Yeah, the reason is because this energy is being stored or released by either the breaking or formation of chemical bonds. And since we're heating the substance here, we are breaking chemical bonds. So that is why we have a constant temperature over time. So just some definitions. Breaking chemical bonds means that energy is being absorbed by the substance, In chemistry terms, we would call this endothermic. You don't necessarily need to know this for IB physics. When we're forming chemical bonds, energy is released, and that is what is called an exothermic process. And a nice way to think about this is pulling magnets apart. You have to force the magnets apart, so you're adding energy to the system. And when you put the magnets back together, they snap. They make an audible sound, and that's releasing energy. So this is kind of a good model for thinking about your bonds. Okay, so this is what you're going to see typically for IB physics, but in reality, our transitions are a little more gentle, as we see here. So we have curved transitions, but we like to keep things simple. We like models in physics. So also the slopes of the graph will tell us some interesting information, and having a specific amount of time during which our substance is undergoing a phase change is also useful. So so these slopes and this amount of time for the phase change, both of those are going to be important when you're working problems. So keep that in mind. All right, here we have a substance cooling. And if we assume that the rate of energy transfer is the same as our previous chart, then these slopes should be the same, and the amount of times for our phase changes should also be the same. Okay, so we've just got a mirror image of our previous chart. Okay, so we're going to define heat now. Energy that's transferred from one place to another is called heat. Wow, that was easy. This is a result of temperature difference. And note that heat only moves from high to low temperature. Okay, so high to low. You may have held your hand up to a window in the winter and felt that the window was kind of radiating cold, but what it's actually doing is pulling heat off of your hand more quickly, and that feels cold. But this is kind of non-intuitive, actually, but true. Okay, we're going to define a term called heat capacity here, and this is the amount of energy required to change. Oh, I've got a typo here. I'm going to fix it. Required to change the temperature of an object by 1 Kelvin or 1 degree Celsius. So its formula, it is formula, jeez. That's right. I don't edit, guys and girls. Professional. Okay, so its formula is this. Heat capacity, C, is equal to a change in energy divided by a change in temperature. So that gives us a delta Q divided by delta T. So there's our heat capacity. This is not necessary for IB physics, but we're going to find that it's useful enough that it's worth defining. So, so this is for a single object. So our unit for heat capacity is a joule per Kelvin. And here's a convenient way that we can rearrange this equation. So our heat energy Q is equal to capital C times delta T. Note that this capital C is very important because in a minute we're going to be dealing with a small c. Sorry for the confusion. I don't make the variables. Okay, so specific heat capacity of a substance is defined by the amount of energy required to heat 1 kilogram of the substance by 1 Kelvin. So now we've added a specific mass to our equation, and this is going to be, excuse me, the primary difference between specific heat and specific heat capacity. Before, in the case of specific heat, we're just looking at an object, but here we're looking at the mass of a substance. Okay, so specific heat capacity then is defined, and note that here we have our small c, not a capital C. This is defined as energy per mass times change in temperature. Okay, there we go. So different substances are going to have different specific heat capacities, and that is because they will have different chemical bonds. The length of the chemical bond between substances is different, and that will affect how much energy they can store. See more in IB chemistry for more information. The data booklet here gives Q equals mc delta T. So our energy is equal to mc delta T. There we go. Here are some examples, specific heat capacities. And you should note that density is not the critical feature for high specific heat capacity. Water here has the highest on this particular chart, and in fact, water is generally one of the highest around, period. It's not the highest, but it's very, very large. And that's due to the fact that water has a special type of chemical bond that we don't need to discuss here, but that chemical bond is more important than the density of the substance. All of these are more dense than water, will sink in water, but this has a much, much higher specific heat capacity. Okay, so we're going to talk about the first law of thermodynamics, where energy cannot be created or destroyed, and you probably already know this. It has to be conserved, so this is by definition a law of conservation. So what that means is that energy into a system must equal the energy out of its system. And when we're talking about heat transfer, that means that the energy that this object loses must equal the energy going into this object. Okay, so for heating and cooling substances, then exchanging energy, we get the energy of heating equal to the energy of cooling. And if we have a heat transfer between substances 1 and 2, we're going to now have this equation. Okay, so this is a starting point for calculating, I mean, it could be any one of these values, but change in temperature is one of the more tricky ones, as we're going to see here in a second. Okay, so if we add an additional cooling substance to our previous equation, then we could get something like this. Okay, so mc delta so the energy of one substance, this is our heating substance, is going to be equal to the energy of our two substances that are cooling. Okay, and we could take a similar approach with the third substance that's heating up. We would just add a term on this side of the equation and get rid of one of these. So you're not usually going to see more than 3 terms at one time, fortunately. So a quick algebra tip. When you're doing your calculations, you're going to find that you're moving these variables around a lot when you're doing the algebra, and that can be pretty annoying. So we can simplify things by using specific heat. So here is M1, C1 equal then to C sub 1, our specific heat. So we just combine these terms into one term, and that just happens to be equal to specific heat. So super convenient. So in order for our energy to be conserved, not concerned, the sum of energies has to be 0. Okay, so that means that one of these is going to be negative, and we'll have something like this. So we have the energy of our heating minus the energy of our cooling, then equal to 0. And we have to do a little trick here with our temperatures in order for this scenario to occur. Okay, so here's our temperature trick. The change in temperature for a heating substance will be given by the change in temperature is equal to final temperature minus initial temperature. And this is the way that we normally calculate changes in stuff. This could work for just about anything you wanted to calculate a change in. And we're just using it for temperature here. Okay, and again, just quickly defining variables. For a cooling substance, though, we need to start with our initial temperature, and we need to subtract from that our final temperature. And this step is going to produce the values we need to conserve energy, because we're going to need the energy over here to be a positive value. And if we calculate temperature the normal way, it'll be negative, and that's going to mean we're adding these two values together. That's going to produce a non-zero result, and that's not acceptable. So we would be violating our conservation law. So our cooling temperature should be our initial temperature minus our final temperature. And again, that's not normally the way we do things, but we have to do it this way here. Okay, latent heat. While a substance is changing phase, its temperature doesn't change. We notice that. And that means that we can't use our previous equation. So every substance has a different latent heat of vaporization or condensation and fusion. So latent heat of fusion is for melting or freezing. Latent heat of vaporization is for vaporization and condensation. Okay, so latent heat is the energy required to state the state, required to change the state of 1 kilogram of a mass of a substance. I'm a professional YouTuber, guys. Professional. Remember, it's poorly monetized. So latent heat L is equal to our energy divided by our mass. So your data booklet shows this equation as Q, heat energy, is equal to mass times the latent heat of either vaporization or fusion. It doesn't matter which one we plug in here. It just depends on the change of state that is occurring. All right, so we're going to look at some examples of latent heat of fusion where we have melting and freezing, and vaporization where we have condensation and vaporization or boiling. Okay, and there are a couple things we should notice right away looking at these examples. The first is that these values are not the same. Okay, so for water, ethanol, and aluminium, our latent heat of fusion and our latent heat of vaporization are two very different values. Okay, what we notice here is that the latent heat of vaporization is typically larger than the latent heat of fusion, and in some cases enormously larger. And that's because our gaseous molecules have a lot more energy, as we're going to see a little bit later in topic 3.2. Okay, so let's put this all together. You're going to be required to consider temperature change time and energy involved as a substance heats or cools through these phase changes. So in other words, we could start like right here, and you'd have to calculate all the energy involved up to this point. So what would that look like? Well, we'd have to consider both specific heat capacity and latent heat in order to calculate the energy involved. So here's an example equation. Here we have mass times the latent heat of fusion plus mass times specific heat capacity times change in temperature. And we have mass times the latent heat of vaporization. So this is the energy involved in melting a liquid and then boiling it away over a period of time. Okay, so here we have our melting, our term of energy for melting, and here we have our term of energy for heating the liquid, and we have our term for vaporizing the liquid or boiling it off. And our mass here is going to be the same every time, which is pretty convenient because we could actually factor out mass if we wanted to algebraically. Okay, final points. When we're working problems, we're going to usually ignore this, but anytime we're transferring energy from one place to another, there's going to be a loss of energy to the environment. Okay, that's going to happen. You can prevent it with good insulation, but no insulation is perfect. Okay, and you will lose energy. It's one of the laws of thermodynamics. Okay, when you're conducting your own experiments, particularly if you know the amount of energy going into the system, this is going to be extremely obvious. If you do an IA that involves heat transfer, you need to consider that energy loss in some way. And I should warn you that controlling temperature is very difficult. And if you can't control it, the least you should do is measure it. Okay, so here are the sources for this presentation. As usual, the excellent Physics for the IB Diploma by Tsokos. I used Wikipedia quite a lot. Here are the pages that I used. Make sure that you donate to Wikipedia if you use it as often as I do. I also use Google Slides, LaTeX, Desmos.com, and Adobe Illustrator. Do not click like, do not subscribe, I guess, unless you really have to, and you should have a great day. Take care.